Number 52. Evaporation of sweat requires energy and thus takes excess heat away from the body. Some of the water that you drink may eventually be converted into sweat and evaporate. If you drink a 20-ounce bottle of water that had been in the refrigerator at 3.8 degrees Celsius, how much heat is needed to convert all of that water into sweat and then to vapor? Note, your body temperature is 36.6 degrees Celsius. For the purpose of solving this problem, assume that the thermal properties of sweat are the same as for water. Okay, so talking about drinking a pretty cold bottle of water, 20 ounces, and for simplicity of the math and the calculations, we want to know how much heat is needed to convert all of that water. So all of the mass that we're going to be drinking, this person must be very hydrated. So all of the water that is being basically drunk is going to leave the body via sweat and then vaporize. So we just want to find out how much heat costs for that 20-ounce bottle to basically come out as sweat and then to vapor. Now, when we're talking about heat, right, heat is a unit of Q. Now, there's two equations that have to deal with Q, which are labeled down here, which we will get into before, but we should always pay attention, especially when we're dealing with heat questions, if we are phase changing in any sort of way. Now, in this case, we are starting off with a 20-ounce bottle of water, and that 20-ounce bottle of water is always going to be in the liquid form, right? And we know that it's in the liquid form because it's above the melting temperature, which is 0 degrees Celsius. So we're at 3.8 degrees Celsius. So we're starting off with liquid, and then we're converting it into sweat, and then to vapor. Now, vapor gives you the clue that this is going to be turning now into the gas phase. So we now have two different phases. And whenever we have two different phases, or three different phases, we should write a roadmap for this question. And the roadmap always consists as the beginning temperature that they talked to you about and the end temperature. So in this case, once you drink that bottle of water, the bottle of water started off at 3.8 degrees Celsius. So I'll write that down. So we're starting off with 3.8 degrees Celsius. The bottle of water came out of the refrigerator, very cold, and was drunk. Now, it's got to climb. It's going in the body, so it's going to get as hot as body temperature, right? Which they said over here was 36.6 degrees Celsius. And now, at that point of the game, the 36.6 degrees Celsius, it's going to start turning into sweat. So we'll put sweat here. But now the sweat, it says, is once it starts turning into sweat, it's going to start evaporating and turn into vapor. So at this stage of the game, maybe I'll put like a little line down here, that once it turns 36.6 degrees Celsius, we can view it as the phase change of the sweat turning into the vapor. And they said that assume that the thermal properties of sweat are the same for water. Whenever you say that it's water and not steam or ice, this is always the liquid version. So technically, for our case and purposes, this sweat is still classified as a liquid, H2O liquid. Just makes the math easier. And then once you hit the 36.6 degrees Celsius over body temperature, you're going to start producing sweat, and then it's going to be starting to evaporate off the body. So this is where your liquid will turn into your gas. Now, seems like we have two things to do. We have to get that energy or the heat to go from 3.8 degrees Celsius to 36.6 degrees Celsius. All the while, this will be H2O in a liquid form. we didn't reach 100 degrees Celsius or 0 degrees Celsius, which are the two important temperatures for water. It's all going to be a liquid here. And then we just have a phase change. So let's work in steps. Step 1 is going to be requiring all the heat energy to just raise that up to the 36.6 degrees Celsius. So let's start it off there. Step 1 is we're going to start at 3.8 degrees Celsius and go to 36.6 degrees Celsius. You say to yourself, is this a temperature change or a phase change that's going on here? Yeah, this is a temperature change. And temperature change, you're always going to use Q equals ms delta T. Or you could use Q equals mc delta T. Preference, it's up to you. I just like to use S because S is for specific SS, specific SS. So, doesn't matter though. Q equals ms delta T. Okay, so we're trying to find out the heat, right? How much heat is required? The heat is the Q, which means that I should know the ms and the delta T. Now the M stands for the mass, and that should be in grams. But they told us that we had a 20-ounce bottle of water. So let me actually just pull this up because I might need a little bit more room. So the first step is that we have to convert the 20 ounces into grams. Now, how do we do that? Well, just know that 1 fluid ounce equals 29.5735 milliliters. We can go from ounces to milliliters, and then we could think of the density to get to the grams. So the middleman over here would be to get to the milliliters, and then we can go up to grams using density. So, let's see, 20 ounces. If we're doing dimensional analysis, we times by a ratio. Put the unit that we don't want on the bottom. Ounces go on the bottom. Milliliters goes up on top. And the conversion is 1 ounce equals 29.5735. Ounces cancel out. We're left with mils. Now, remember that the density of H2O liquid is always 1 gram per 1 mil. So whatever the grams that you have is the actual amount of milliliters that you have. So from right here, if I just equal this and just see how many milliliters I have, that would be the same as many grams as I have, because the density is always a 1-to-1 ratio. So let's see, 20 times 29.5735. Numbers look good? Numbers look good? We got 591.47 milliliters. And because of the density, we have 591.47 grams of H2O. And now I know that that mass is 591.47. The S value is the specific heat of the water, right? We're in a liquid phase, and the liquid specific heat is 4.184. 4.184 joules per gram times Celsius. And now delta T is like a formula in itself. I'll put it up here. Delta T equals your final temperature minus your initial temperature. So for your two temperatures that you're changing, the initial is always your TI, so the 3.8 is your TI, and the TF, your final temperature, is the 36.6 in this case. So TF minus TI, 36.6 minus 3.8. So 36.6 minus 3.8 looks good to me. I got 32.8 degrees Celsius as my delta T. So now I'm ready to go. I guess, let's see, maybe I can get some room in here. maybe I could do it over here. Q equals M S delta T. So my M is 591.47. My S value is 4.184, and my delta T is 32.8. So let's find out the heat that is required just for that temperature change. So it's this number, press enter, times 4.184 times this number. Take that. Everything looks good. Looks good to me. Press enter. A lot of joules. 81170.5, I guess. And this is in joules because the specific heat unit had joules in it. So joules goes with joules. Okay. So step 1 is done. We have officially found out the amount of heat that was required to just get that water up to 36.6 degrees Celsius. 81,170 joules. Crazy. Okay, now it's turning into sweat. Sure. But then the sweat is going to evaporate. So here's my step number 2. We have to get that liquid, aka the sweat, going into the gas. So let's write that out over here. Maybe I'll draw like a little line here. Step 2. We're taking the liquid, aka the sweat, but they did say that it has the same thermal properties, and going to the gas. Maybe I'll just put sweat here in parentheses. So you say to yourself, is this a temperature change or is this a phase change? Yeah, there's no temperature here. This is a phase change. And for phase changes, you use the other formula. Q equals N delta H vaporization. We're still trying to solve for Q, which means that we should know the N and the delta H of vaporization. Now keep in mind that this is talking about sweat, but we're still talking about water. Now the N in this case is not the M. The N is moles. So now we have to find the number of moles of the water. But that's okay because we found out that we had 591.47 grams of H2O, and I can just convert it to the moles of H2O. Now you can do dimensional analysis if you want to, but just remember that grams to moles of the same compound or the same molecule, all you have to do is just divide by the molar mass. So whatever H2O is on the periodic table. So on my periodic table, there's 2 hydrogens, each one weighs 1.008, and then I'm just going to add the 1 oxygen. On mine is just clear as 16. So you get 18.016, so I'll just divide by 18.016. So we'll take this number that we had all the way in the beginning, press enter, times by this number. Gotta love the TI-84. Less chance of error. And just making sure that everything looks good here. And I'll press enter. Whoa. I got a lot of moles. And I found my mistake. You might have been screaming at me. I pressed multiply. We should have divided. There you go. And let's just press enter. Okay, that's more realistic. So my moles is 32. We'll say 83. Okay, so 32.83 moles. Now I know that that's my N number. 32.83. And my delta H of vaporization, my enthalpy of vaporization, comes from the standard number for water, which I wrote down the standard value here. It's 40.66 kilojoules per mole. And that's also why moles has to go with moles. So your unit of quantity should go together. So in this case, we have Q equals N times the delta H. My N value is 32.83, and my delta H value is 40.66. Okay, Q equals. I'll just take the total number up here, because technically it's not the final answer, so shouldn't really round that much, times 40.66. Okay, we get 1334.9 kilojoules. All right, so that's the amount of energy that's needed to just turn that sweat into vapor. But we completed the second step. No more steps to do. But now they asked how much heat is needed to do the whole thing. I needed to convert it into sweat, and then I needed it to vaporize. So what are we going to do with these two Q values? Yeah, we're going to add them together. But there's a catch. One is in joules, and the other is in kilojoules. You have to first convert one to the other. Now, does it really matter? Not in this case, because they didn't say what unit they specifically wanted it in. But since we're dealing with big numbers here, I'm going to convert the joules into kilojoules. So first things first is just, I guess, pause the video if you need to write out these formulas here. But I'm just going to erase this little box just so that we have enough more room. And now, I'll just say over here, add Q values together. But before we do that, we just have to convert that first Q value, and I'll convert it into kilojoules. Remember, joules to kilojoules, all you have to do is just divide by 1,000, or similarly, you could just take the decimal, move it over to the left 3 times. So this would be 81.1705. 81.1705 kilojoules. Maybe I'll just highlight that as well. So now I'm going to add up 81.1705 kilojoules plus the 1,334.9 kilojoules. And what do we get? So 1,334.9 plus 81.1705. Press enter. There we go. And 1416. But now, if you want to play the sig fig game, I don't know. We're all over the place here. I mean, technically they said 20 ounces, so that's only 1 sig fig. So I guess it doesn't really matter here. I'm just going to say 1420 if we rounded it. And this would be in kilojoules. And that is the final kilojoule. This is the total heat. And that is the final answer. Okay, what'd you think? Hopefully this helped you out. Let me know in the comments. Thank you so much for viewing the video and for being part of this community. I'm so glad that these videos are helping you out in your chem class. We also have physics and math videos on the channel to help you guys out within those classes as well. So go check the channel out. I hope you're all doing well, and I hope you have a great, great, great day. Talk to you soon. Bye-bye.